Pythagoras' theorem applies to right-angled triangles like this one. This triangle has sides A, B and C. Side C is the hypotenuse. The hypotenuse is the side that is opposite the right angle. It is also the longest of the three sides. Pythagoras' theorem is a formula that relates the lengths of the three sides. It tells us that c squared is equal to a squared plus b squared. There are many ways of proving this. In this video we will look at two proofs. The first is a visual proof, the second uses algebra. We can prove Pythagoras' theorem visually. We take four identical copies of the right-angled triangle and form them into a square like this. This arrangement of triangles forms an outer square with sides of length a plus b. It also forms a yellow square in the middle with side length c, formed by the hypotenuse of each triangle. This square has area c squared. We can rearrange the blue triangles to form two rectangles, each of size a by b. In this arrangement, the yellow area can be divided into two squares. One has side length a, so its area is a squared. The other has side length b, so its area is b squared. Since the area of the outer square hasn't changed, and the area of the blue triangles hasn't changed, it follows that the yellow area must be the same in each case. This means that the old area, c squared, must be equal to the new area, a squared plus b squared. This proves the theorem. With a visual proof, we need to make sure we aren't making any assumptions. For example, are we sure the two squares in the proof are really squares? For the outer square, the sides are made up from two sides of the triangles, so each side of the square has length a plus b. We know that the four angles are right angles because they are formed from the right angles of the triangles. If the sides are all equal and all the angles are right angles, it must indeed be a square. For the yellow inner square, we know that all the sides are equal because they are each formed from the hypotenuse of one of the triangles. So every side has length c. Also notice that the whole diagram has rotational symmetry of order 4. We will mark the top left angle of the yellow square. If we rotate the shape by 90 degrees, the whole shape maps onto itself. This proves that the angle at the right of the square is equal to the top angle, because one maps onto the other. If we rotate it again, it proves that the bottom angle is also equal. If we rotate it a final time, it proves that all four angles are equal. Since the angles of a quadrilateral add up to 360, if all the angles are equal, they must be 90 degrees each. Since the sides are also equal, this again proves it is a square. This second proof uses the same diagram as the visual proof. This time we will calculate the total area of the large square in two different ways. The first way to calculate the area is to use the side length of the square, which is a plus b. The area is the square of a plus b. Multiplying out the brackets gives a times a plus a times b plus b times a plus b times b. We can simplify this equation since a times b is equal to b times a. This gives us the final area A equals a squared plus 2ab plus b squared. Now we will calculate the area in a different way. This time we will add up the areas of all the parts that make up the square. There are four blue triangles and one yellow square. The area T of one of the triangles is half height times base, which is half AB. The total area A is equal to the area of the yellow square, which is c squared, plus 4 times the area of the triangle. That is c squared plus 4 times half AB. This simplifies to c squared plus 2ab. Now we have two different ways to calculate the area A of the big square. One is a squared plus 2ab plus b squared. The other is c squared plus 2ab. We know these two areas must be equal because they both represent the area of the same square. So we have this equation. We can cancel 2ab from both sides, which gives us c squared equals a squared plus b squared. So this method also proves Pythagoras' theorem. If you enjoyed this video, please subscribe or visit graphicmaths.com. The link is in the description below.